Hi! In this video, I'd like to practice graphing functions using transformations with you. In a previous video, I talked about the variety of transformations that are very common, and I have them listed here. In this video, we're just going to practice problems, so let's get to it. For my first example, I'd like us to sketch the graph of y equals the absolute value of x minus 4 plus 1. So let's look at our base graph or our parent graph first. We know that the absolute value graph is one that would look like this, right? Looks like a V with slopes 1 and -1. Well, for this one, we see there are two transformations that have happened. We see here we have an x minus 4. Remember, when the number is associated with an x, the translation is in the x direction. And this one will shift to the right 4. Yes, to the right. It feels backwards to people at first when they're first learning. And this one means we move up 1. So I'm going to draw my grid. And I'm going to consider this key point right here that was at the origin, and I'm going to move it right 4 and up 1. So 1, 2, 3, 4. Make sure that's very clear to the reader, and up 1. And then I would very carefully draw this line, or part of a line, with slope 1, and this with slope -1. And this rough sketch is done. Of course, you could plot some more points or label the y-intercept. And if you needed to, you could go ahead and do that. But as a rough sketch, we have the essence of the graph. Let's move on to the next one. We're sketching the graph of f of x equals -1 over x minus 3. Do you remember that the parent graph or the base graph for y equals 1 over x looks like this? We have one branch up here and one branch down here with horizontal and vertical asymptotes that on this graph are on the x-axis and y-axis. So if we shift this graph up or down, right or left, we must include those asymptotes when we do it. But let's jump in. Let's start with this transformation first. The negative in front of the function, right? When we make this a -1 over x, remember we're going to reflect the graph across the x-axis. So we could still on our scratch paper, I'm just thinking over here, think about y equals -1 over x, and my graph would look like this. This top portion or top branch would come down here. And this branch of my hyperbola, this is called the hyperbola, would come up here. So let's draw that. So I've taken care of that reflection, but now I'm going to handle this. This tells me that the graph has been shifted down 3 units. So I'm going to make sure that this horizontal asymptote right here gets shifted down 3. Let's take care when we draw that. So here's my grid, or my axes, and I'm going to draw a horizontal asymptote down 3. It was at 0. Now it will be down here at -3. And we draw in that horizontal asymptote with a dashed line. Now the vertical line, my line does not look very vertical or doesn't look very straight, is right here. And you often don't see the asymptote if it's actually on an axis. So now I'm going to draw my branches of my hyperbola. Let's see, I often just go over 1 and up 1 unless there was some stretch for the graph. And now I can draw my branch. I make sure it goes up toward this asymptote and down toward this one. And similarly, I'll start with this point right here and I'll curve it toward the horizontal asymptote and toward the vertical asymptote. And I have this graph complete. Here's our next one. We're going to sketch the graph of y equals the square root of the opposite of x plus 5. Remember, our base graph or our parent graph for this one would be our square root graph. I hope you remember that this one looks like this. It's that half of a parabola on its side. Remember, it has a restricted domain because we want to take square roots of positive numbers only. But notice what happens here. We have a negative inside, and when we have a negative in front of the x, remember it's going to be a reflection across the y-axis. So if we were going to graph y equals the square root of negative x, our graph would look like this. And I hope that makes sense to you, because notice right here, because of this negative, we must substitute negative values in, because the opposite of a negative number would be a positive number, and that's what will be important. So we have taken care of the square root of the opposite of x, but now we have a plus 5 added to the function. That means it's a shift up 5 units. Let's do that. And we'll answer it officially right here. So we have this graph on the lower left that we're shifting up 5 units. So I will put my point right here, and I'm going to draw my half of a parabola off in this direction. And again, if need be, you could plot some points if you needed a graph that was a little more precise. But we have our nice rough sketch. Let's make sure that it's clear what the domain and range are for this one. Remember, we can just look at our graph if we see a picture. The domain are the x values for which the function is defined. And notice from left to right, the function exists over here, and then it stops at 0. In other words, negative infinity up to 0 is our domain. And we'll make sure that we close it at 0, because 0 is an acceptable substitution into the function. And we might as well write our range. Our range are the y values for the particular graph or the particular function. Notice from bottom to top, there's no values down here. There's nothing on the graph until we get up to 5. And then it goes up, and it will continue going up forever. So our range begins at 5, and it heads up to infinity. So we should be able to do something like that or be able to state something like that for a function. State its domain and range. Let's look at the next one. We're going to sketch the graph of y equals 6 minus x cubed. Now, I want to point out that I have it written this way, but you could rewrite it like this. The opposite of x cubed plus 6. I find that often when people rewrite it, they see it a little bit easier if they put that x cubed first. So, do you see what happened with this particular function? We have a negative in front, so we're going to reflect across the x-axis, and we're going to shift it up 6 units. So our y equals x cubed graph, let's make sure you remember what that is. Y equals x cubed is our graph that looks like this. It goes relatively flat right here at the origin. It's not completely flat, but to our eye it goes almost horizontal. So we're going to make sure we reflect it across the x-axis. So we'd have y equals negative x cubed that would look like this. See, I didn't make it quite flat enough there. And then we're going to shift it up 6 units. So our graph would look like this. Right up here at 6, and I make sure I draw that shape. So anybody reading my graph could tell which function we're talking about. And that one's complete. If we were asked for the domain and range on this one, notice the domain is the set of all real numbers. You can't tell very well from my graph, but this graph does not go vertical. This is actually not going straight down. It is very steep, but it in fact keeps going to the right forever. Similarly, this one is moving to the left forever. And if you look at the equation, you can tell right here, right here. What numbers can you substitute into this function? Well, any real number would be acceptable. So our domain is negative infinity to infinity. And our range, those are the y values that are a result of putting in those x values. And our range is also from negative infinity, because it's heading down here, up to positive infinity. Let's look at this one. We're going to sketch the graph of y equals 1 over x plus 3 plus 2. Do you remember what your base graph or your parent graph looks like? We're talking about the function y equals 1 over x. So it's our hyperbola. It looks like this with those two branches with two asymptotes. And those asymptotes are going to be relevant for this problem. Notice because of this x plus 3, my graph will be shifted left 3. And because of this plus 2, up 2. Left 3, up 2. So I'm going to draw the asymptotes in, and they will be my graphing guides. So when I move this graph or shift the graph left 3, I will have an asymptote right here. Let me put it in red. At negative 3. And notice that corresponds to the number that would be that would make this undefined, the number that is not in our domain. And we're going to shift up 2. So let's put our horizontal asymptote in at 2. And now I just use those asymptotes as graphing guides. My graph must approach the asymptotes. So I'm going to start at this point, and I'm going to go over 1 and up 1. That's, as I mentioned before, a nice starting place. And I draw a curve toward those asymptotes. And similarly over here, I would have my rectangular hyperbola that looks like this. Again, if you're required to put in more detail, like the x-intercepts and y-intercepts, you can substitute in zeros and find those values. I'd like to just do one more thing, and that is state the domain and range. And I'm going to erase this, make a little bit of space here for these for this particular function. So let's talk about the domain. Remember, the domain is the set of x values for which this function is defined. And this function is defined from negative infinity to positive infinity, except for negative 3. There is no value here at negative 3. And notice up at the equation, we can see that. The function doesn't exist at negative 3. So we would say our domain is negative infinity to negative 3. Union negative 3 to infinity. And how about our range? Where are the y values? Where do they exist? Well, notice we have y values down here to negative infinity, all the way up to positive infinity, except for right here. Notice there's a little gap right here at 2. There is not a point on this line. So our range would be negative infinity up to 2, union 2 to infinity. Let's ask a little bit different question now. Suppose you're given the graph of a function. So I have a graph of y equals f of x. And now let's graph using our transformation. And the function that we're going to be asked to graph is y equals 1/3 f of x. So our job is to look at this 1/3 and figure out what it does. Remember, a coefficient of the function will be a multiplier and will either stretch or compress the graph vertically. So it will compress the graph by 1/3. So our y values will be 1/3 as high. So here's what it looks like. I'm going to take the point at -3 and 3 and leave them right where they are. But everything else will be compressed to be 1/3 as big as it was. So -3 is now at -1. This point right here that was at 6,3 is now at 6,1. And I'm just going to some of my key points. This point was at 9,3. It's now at 9,1. And notice all of my points are 1/3 as high as they were previously. And so my graph would look like this. Notice only the y values have changed. The domain is still exactly the same. Now, if you have a problem visualizing it, one thing that you could do for this particular problem is take your old coordinates. So I'm going to put some of the key points down here. -3, 0, 0, -3, 3, 3, 6, 3, and 9, 3. And you can simply multiply the y values by 1/3. If we do that, we'll see where the new ordered pairs would be. We'd have -3, 0 times 1/3. 0, -3 times 1/3. 3, 3 times 1/3. 6, 3 times 1/3. And 9, 3 times 1/3. Our stretch or compress factor right here multiplies our y values by 1/3. And our ordered pairs become -3, 0, 0, -1, 3, 1, 6, 1, and 9, 1. And you'll notice that these points right here are the key points that I have graphed. Let's look at another one. Let's do another one. We'll use the same graph, but now we're going to graph the related function that is p of x equals f of 2x. Do you remember what this constant does when it's multiplied by x? Remember, that's a stretch or compress in the x direction. And in fact, a 2 here means our multiplier is a half. We're going to compress toward the y-axis. We can multiply our x coordinates by the reciprocal of that coefficient, much like we multiplied the y coordinates in the previous problem. So let's do that. My ordered pairs are, again, -3, 0, 0, -3, 3, 0, 6, 3, and 9, 3. And those are just the key points for the graph. Now I'm going to be multiplying the x coordinates this time by the reciprocal of this number. So we're multiplying by a half. So we have 1/2 times -3, 0. 1/2 times 0, -3. 1/2 times 3, 0. 1/2 times, whoops, times 6, 3. And 1/2 times 9, 3. So those ordered pairs become -3/2, 0, 0, -3, 3/2, 0, 3, 3, and 9/2, 3. Let's plot these on our graph. So -3/2, 0 is -1.5, 0. We have 0, -3. We have 3/2, 0. We have 3, 3. And we have 9/2, 3, which is 4.5, 3. And now we'll draw in our graph. And it looks like this. So notice we have the same shape, sort of, but it's been compressed or pushed toward the y-axis from both the left and the right with this factor of 1/2, or our multiplier, I'll say, of 1/2. And this one is done. Let's do another one. In this one, we'll still use the same function, but now we're going to transform it in this way. We're going to graph h of x equals f of -x. Do you remember what that -x does? Right, it's a reflection across the y-axis. So we can do that reflection. I'm going to just go point by point with our key points. So here we go. This point that is at 3, 0 would go to -3, 0. This point that's at -3, 0 would go to 3, 0. This point right here wouldn't go anywhere. So far it hasn't been too exciting. But now look at this point over here. This point right here at 6, 3 would come way over here to -6, 3. This point at 9, 3 would come over here to -9, 3. And now I can draw my graph. Make it clear it stops right here. Got to draw it a little bit thicker so you can see. And there is no point right here at 6, 3. My pen made a little mark there, but that's not a piece of our graph right there. Okay, so there's our picture. And I hope you can see that it's a mirror image across the line that is the y-axis. If you were going to do a point-by-point translation or transformation, you could do that. You would just multiply the x values by -1. For example, you could take the point 3, 0, and when you multiplied the x value by -1, you'd have -1 times 3, 0, which would go to -3, 0. Similarly, you could pick the other key points and multiply your x values by -1. I just like the visual, but you can do it manually, point by point, if you'd like. Again, picking some of those key points. Let's do one more using this same base graph. So I'd like to graph q of x equals f of x minus 3 minus 1. Let's look at what our transformations are. Notice we have an x minus 3. That means the graph has been shifted right 3. And then we have this minus 1, so it's shifted down 1. So I'm going to take those key points and shift them right 3 and down 1. So let's do it. Starting at this point, -3, 0, it's going to shift right 3, down 1. I'm going to put the point here. Here's another key point. Right 3, down 1. Here's another key point. Right 3, down 1. Right 3, down 1. I wish I had my grid a little bit different. So right 3, down 1. And my graph looks like this. and it's complete. We're going to look at this kind of a problem. Suppose it says if negative 5, 3 is on the graph of f of x, what point can we conclude must be on the graph of y equals negative f of x? Now, we could memorize formulas, but I just want to look at the graph. I hope you know at this point that this means there's a reflection across the x-axis. So I just look at a picture, make myself a picture here, and here's a negative 5, 3. There's the point they're talking about, and you can even give yourself a picture that is a function. I could draw that. That's a kind of a sloppy looking function, but it's a function nonetheless. And if I looked at that and said, hey, the graph needs to be reflected across the x-axis, I know any point up above the x-axis would go below, and any below would go above. So it would look like this. So the relevant part is that this key point here is now down here. And I can just look at my graph and say, hey, it must be at negative 5, negative 3. And you can see what has happened. We multiplied the y value by negative 1. So my answer would be negative 5, negative 3. What if they said that negative 5, 3 is on the graph of f of x? What can we conclude must be on the graph of y equals f of 1/5 x? What does that mean happen to the function? Remember, this is our horizontal stretch, and we multiply by the reciprocal of this, and it's going to be stretched out. So if I drew my picture again, and this is just me thinking it through, I know I had this point right here at negative 5, 3, and I just drew some somewhat random function just because it helps me think it through. And I'm thinking this is getting stretched way out. So this one is now way out here. This one is way out here. This point would be unchanged. This would be way out here. And this would be way out here. I would have a graph that would look something like this, but they specifically are asking about this point, negative 5, 3, right here. What happened to it? Well, it went from here to here. What changed? Well, the x value changed, and it changed by a factor of 5. This point right here, whoops, let's do it in blue, is at 5 times negative 5, comma 3. My y value is unchanged. It's our x value that's changed, multiplying by the reciprocal of this number. So now I'm at negative 25, 3. And that would be the answer to this question. So if you're asked questions like this, I would encourage you to draw yourself a picture and get practice looking at the transformations on our functions. Let's do one more problem. Here it is. Suppose that the x-intercepts of a function are negative 3 and 11. What are the x-intercepts of the graph of y equals f of x plus 4? And again, they didn't give us a picture to look at. But let's draw one where negative 3 and 11 are the x-intercepts. And I don't know what the function looks like. It could look something like this. We don't know. But what we do know is what's happened to the function. We have f of x plus 4. X was replaced with an x plus 4. Do you remember that that's a horizontal shift? And with this one, it's going to be a shift left 4. So instead of having my x-intercept at negative 3, I'm going to shift left 4. And where will that put us? Do you see that we'll be here at negative 7? And we were at 11. And we shift left 4 here, and that will put us at 7. So the answer to this question is the x-intercepts will be at negative 7 and positive 7. What if they asked us the same type of question, but they said, what are the x-intercepts of the graph of y equals negative f of x? I kind of like this one as our final problem. So again, I'm going to draw my picture. The x-intercepts are at negative 3 and 11, and that's really all I know. The graph could do something like this. We don't know. All we know is that it has x-intercepts at negative 3 and 11. What does this negative do? Remember, it's a reflection across the x-axis. So our graph is transformed this way. My points up here will come down here. Oops, let me change to blue. And it will come up and down. Oh, I wish I hadn't done such a squiggly graph here. I'm trying to make a nice mirror image of it. There, something like that. There's my mirror image across the line that is the x-axis. So here's our graph of y equals negative f of x. And notice our x-intercepts have not changed. The x-intercepts are at negative 3 and at 11 still, because this negative would only be multiplying by the y coordinate. And our negative 3, 0 would go to negative 3, comma, negative 0, which is still negative 3, 0. Similarly, 11, 0 would just go to 11, 0. I hope you'll go practice graphing some functions using your transformations.